Lesson 1, Video 3, Limits. So we're going to talk about the behavior of functions a lot in this class, and in order to do that, we need to be clear on some of the language. So to start, when you're talking about the behavior of any function or curve, we like to look at it as if it moves from the left side of the screen to the right side of the screen. So if you take a look, if we were tracing the function here, f of x, that you see, I would talk about this function as if it literally started at the most left and negative aspect of the graph, so I'm highlighting over here, and traveled forward, right, along the x-axis. If we keep that as a static way of looking at this, right, of starting from the left and traveling towards the right, then now we have context to refer to things as increasing and decreasing. So if we're looking at it from left to right, then we would say that this function begins, let's make it a little bit brighter so we can follow along. This function begins as a decreasing function. So notice with the green highlight, it's decreasing because it's going down from left to right. And then at x equals -1, the function is now increasing, reaches a hole, jumps, and then it reaches an asymptote at x equals 2, and now it is decreasing again, okay? And then at 4 it jumps, there's another hole, and it's increasing. So when we look at a function and we read it from left to right, we can refer to its movement as increasing and decreasing. Also, if we're talking about an x direction going on forever, we can say that x approaches negative infinity or x approaches positive infinity. So as you see here, if we show x with an arrow and an infinity sign, we read that as x approaching infinity, meaning as that function continues on forever. Okay, now with some of those basics, given this curve, let's talk about some of the features that we see happening here. So when we talk about a function, we refer to this behavior, this movement, this location, as a limit. Now, what some students get confused about, and rightfully so, what's the difference between the limit of a function and the actual height or y value of that function? So we're going to go through that today, and I think you'll get some clarity. So number 1 says the limit as x approaches -2 of the function f of x equals 0. So this is a statement. I'm going to read that again, and you should pause the video and see if you can write this down so that you get better at how to read a limit. Number 1 reads, the limit as x approaches -2 of f of x equals 0. So what that means is if I take my finger along the function and I trace the function out, as I get closer and closer to x equals -2, does the height of the function get closer and closer to 0? Well, let's take a look. I'm going to zoom in. So, as I get closer to the x value of -2 from the left side, my function gets closer and closer to 0. As I approach it from the right side, the function still gets closer and closer to x equals 0. So since it does the same thing from both the left and the right, I can say that the limit as x approaches -2 of f of x does indeed equal 0. It just so happens that that's also the function value. F of -2 is also 0. So let's write that down. F of -2 equals 0. So we have a limit and a function value, both as x gets closer to -2, that equals 0. So right now, I don't know that we can say what the difference is between a limit of a function and the function value. Let's try number 2. We read this one as the limit as x approaches -1 of f of x does not exist. You'll also see that noted as DNE going forward. So let's see what's going on. Let's go to the graph again. Let's look at -1. So I'm looking at -1, and what I notice is as my function gets closer and closer to the value -1, I do see from the left side, we're going to draw this out, from the left side, x approaches -1,
if I trace that function, it's getting closer to a
y value of -1. If I look at it from the other side, if I trace it as x gets closer to -1 from the right direction, notice that the y value it gets closer to is -2.
So, the limit
as x approaches -1 from the left of this function
seems to equal -1.
But, as we saw here, the limit as x approaches -1 from the right of f of x, that seems to equal -2.
So the limit is not the same value from
from the left as it is from the right.
So I have to say the limit does not exist.
But here's the question. Does the function exist when x equals -1? Yeah, it does, because if you look at that function, f of -1 equals -2, because there is a solid circle on that graph.
So here's an example.
Where the function value is different than the limit.
In 3, 4, and 5, you can freeze your screen and try some limits on your own.
You'll notice the limit answers are there. See if you get the same answer when you try those on your own.
On this screen, does the limit exist?
Is the function defined?
Well,
if I trace that from the left, I notice that the function gets closer to the y value of 1. But if I trace it from the right, will the same thing happen? Let's test it out. So the limit as x approaches c does seem to approach +1 as a y value. If I do the same thing from the right, the limit also approaches the height of 1.
So I can say the limit as x approaches
c of this function equals 1.
But the
Value at c, let's take a look. When f is evaluated at c, it actually is 2. Look on that graph. It has a jump discontinuity. So this is a jump. And the function's discontinuous because if you noticed, I can't actually draw the entire function without picking up my pen or pencil. So we can also say that that's discontinuous. So we have a jump discontinuity.
Take a look at this example. Does the limit exist?
Is the function defined? So here we've got x approaching c from the left and going towards what I would say is a -infinity direction. But when it approaches it from the right, it's going to +infinity.
In pre-calculus, you've definitely heard this
Referred to before as an asymptote. So this function has a vertical asymptote when x equals c.
which basically means
That if this function has c in its denominator, such as x plus c, and it can't be factored out, an asymptote will surely be what we see as a graphical interpretation. So here, does the function have a value at c?
no.
Because it's an asymptote. So we would say that not only does the limit not exist, does not exist, but we would say that the function at c is undefined.
Does the limit exist here?
Is this function defined? So again, the limit as x goes to c.
It looks like from the left it approaches
5, and from the right it approaches 6. So I would say the limit does not exist. And the function value at c equals 6.
How about here?
We've got two asymptotes. This sort of looks like a function that's been manipulated, but could have looked like one of our very famous trig functions.
Notice how in this example,
I'm actually asking you to give me the limits
from the right,
or left sides. So let's try that out. The limit as x approaches c from the left. That's the first one right here. We're going to call this number 1. The limit as x approaches c from the left of f of x.
take a moment,
And see if you can answer numbers 1, number 2, and number 3.
freeze your video, take a minute,
And try these out on your own.
Okay, so if you've done these problems,
And you got the right answer, you should see that number 1, the limit as x approaches c from the left. The limit as x approaches c from the left
looks to be 2 units up.
from that x-axis. So we would say this limit equals 2. The limit as x approaches c from the right. Let's take a look. It's the same height, so that also would be 2.
So what if I didn't designate?
Designate whether it's left or right. Well, number 3 says the limit as x approaches c. So that's actually asking me if it approaches the same value from the left and the right. And it does. So we can say 2. And then number 4, we also know the function value at c is 2 because there is no discontinuity. I'm just going to put an axis in here just so it's not confusing. Those of you that were wondering where I was getting those numbers. There you go.
In this example, you're going to notice
That it's not going to work out as pretty. Same function, but now we're looking at the fact that we're evaluating what happens at c, and we're looking at the limit at c when it's an asymptote. So the limit as x approaches c from the left, that's number 1. From the right is number 2.
number 3 is
The limit itself, and number 4 is the function value. Just as you did in the previous problem, freeze the video and try these out.
okay.
Hopefully you froze the video and you took a minute to see what's actually going on here. So number 1, the limit as x approaches c from the left of the function.
Well,
If I trace that, it's clearly going to positive infinity.
the limit as x approaches c from the right.
Side, however, is going in the exact opposite direction. I'm going to call that negative infinity. Since the right side and the left side are approaching different distances, we have to say that the limit does not exist.
What about f of c?
Do you see a point?
At c along the function? You shouldn't. So
F of c is undefined.
let's try this one.
I'm going to coach you again through this by saying freeze the video and see if you can answer 1, 2, 3, and 4 on your own.
Okay, let's check the answer.
The limit as x approaches c from the left of this function. C from the left, I trace the function and I notice it's a little bit above 2.
Just a little bit above 2.
Right?
So we'll say about 2.1.
So 2.1.
How about from the right? Well, clearly this is a discontinuity.
Then the line can't be drawn without picking up your pen or pencil. And it's at the height of 1. So we're going to say the limit as x approaches c from the right is 1.
Since 2.1 and 1 are not
The
the
same number, we know both analytically and graphically that this limit cannot exist. So we're going to say does not exist.
I'm also going to say that the function has to be undefined because
Because there is no point anywhere where x equals c. It's just 2 holes. Again, we call this a jump discontinuity, and it's undefined.
we could do the same thing if we used
If we used tables to find limit values. Watch the next video to see how that can be done, only using the numbers that you get by evaluating a function and without looking at a graph.